Okay, welcome to EGR445 Summer 21. This is the first class, and let me go through the syllabus, also the resources that are available to you on Canvas, and give you some guidelines on how to do well in this class, what is expected, and overall class structure. First and foremost, this class is structured well, and you have lots and lots of resources to look at on Canvas. So let me show you what is available on Canvas. So if you head over to the Canvas EGR445, first and foremost, I want you to take a look at the syllabus. So if you look at the syllabus, this is the syllabus for summer 21. The class is supposed to meet on Tuesdays and Thursdays from 1 p.m. to 4:25 p.m. So it's a long class, but please understand, I plan on giving 1 or 2 breaks in between. So that way you will have some time to get a glass of water or eat something and just prepare yourself. Again, the textbook is this textbook of machine design. Please understand, the newest and the greatest edition of the textbook is not required. Some old editions are available online. You are welcome to use those as reference, but most of the material will be given to you and discussed in class. The objective of this course is the mechanical engineering system design. So how do we design the system, not the components, but how do we combine these components so that we have a fully functional system? Now we will look at different components, selecting components, how to place those components, how to look at the CAD drawings, how to construct different components, geometries, that type of stuff. Now we will apply design principles. We will look at some hardware, software design, and we will look at the software tools. So please attend all the classes. And this class is scheduled as ASU Sync. So we would have meetings via Zoom, but I would be also available on campus all day Friday to answer any questions you may have. So for some students, I'm told that the class timings are not convenient to come to campus. So you are welcome to stop by my office on Friday afternoon or evening, and then I would be happy to go through the material or answer any questions you may have. And please understand, this course is a 11-week class. So you are going to have either the homework or the quiz. And I have given you the deadlines. So please try to follow the deadlines. For some reason, if you miss a deadline, let me know so I can give you an extension. I understand it's a fast-paced class and there could be some unforeseen difficulties in completing the assignments. Maybe your SolidWorks crashed, or maybe you did not have access to some of the material on time. So in that case, just let me know so we can extend the deadline. But please understand, at the end of the class, before the last day of class, all the material should be completed so that your grades can be posted on time. Now, the grading structure, the breakdown is 60% of the grade is based on the quizzes and 40% is homework. And for homework, you are welcome to work in a group and collaborate, but everyone should turn in individual homework, and on quiz, you are supposed to work independently. But in case if you get stuck or if you have questions, you are welcome to send me an email, or you are welcome to use the chat or forum on Canvas. All homeworks and all quizzes are open book, open notes, and most of the problems in the quizzes will be, and homework would be similar to the ones that we worked out in class. So if you follow the material, then you should be able to understand the homework, the quizzes very, very well. And you should be able to do well. Then I just want to tell you one thing. Probably there is a little bit change of perspective here. This is not a math class. So what it means is there is no right or wrong answer for design problems. As long as your design is based on sound engineering principles and you can justify your design, that design is good. And most of the times, what happens is we design something and then there is some sort of iteration or modification based on the thumb rules or experiments, or sometimes the availability of material, component, and cost that dictates the changes in the design. So whatever you do, just try to justify your calculations. That is what is very important. And you will notice that for some designs, there are more than one or two procedures. So ideally, if you look at the design, there is not a unique process to design. And I will try to discuss different design philosophies. And you are welcome to try or follow any one of the design approaches or philosophy that makes sense. Also, please don't try to be late unless there is some valid university excuse. And the drop and add deadline. This is the summer class. So my understanding is today is the deadline to drop the class. So for some reason, if you think this class is too fast paced, lot of material, lot of work in a very short period of time, and or if your situation changes, work, family, some other stuff, and you want to drop the class, just drop it today without any penalty. For some reason, if you get late, then you will have to withdraw from the class. Add drop option will not be available. The next thing what I want to talk about is the class schedule. So this class is designed to be sort of a flipped class. What it means is I have already made the videos and uploaded those videos on YouTube. So what you can do is, this is a suggestion, that before you come to class, if you watch the video, that would help you gain the understanding of material quicker. Or sometimes some students want to accelerate the curriculum. That's totally fine with me as well. What it means is, if you feel comfortable, if you watch the YouTube video, and if you work on the homework and quizzes, you don't have to stick to the schedule. You can work at your own pace. And you are welcome to ask me questions at the end of the class on any of the material. not just the material that we discussed in the class, but for some reason, if you decide to go ahead and maybe look at the design of spur gear, maybe you're working in industry and spur gear is something that you really want to learn about. You're welcome to watch the design lecture on the spur gear, read the textbook, and ask me questions. That's totally fine. So this is sort of, you can pace yourself. So class 1, that is today's class, we will go through the syllabus. We will also talk about the basic concepts, and I will work out few problems. I will talk about the design of levers. I will talk about a design of maybe pins and some other simple design elements. So in today's class, we will talk about simple stresses and design of simple elements. This will be sort of a continuation of your EGR444 class. In next class, we will start looking at the systems, which means designing one or more components which come together and form an assembly. So next class, we are going to talk about design of cotter joint. So I would cover the design of cotter joint, which is chapter 12 from the textbook. After that, we are going to look at design of knuckle joint, which is again chapter 12. Homework 1 is assigned today, and you have 5 days to work on the homework. Now here is my suggestion. As I am teaching, it might be a good idea to just pull the homework and look at the problem. I would be solving similar problems as homework problem during the class. So my hope is that as I'm discussing those problems, take a look at the homework problem and come up with a strategy, come up with a plan on how would you solve the problem. And if you have any questions, I'm going to give you some time at the end of the class, maybe about 30-45 minutes for discussions and question and answer. At that time, you can ask me questions related to the homework and the quiz that is assigned. Say, for an example, you can say, hey, this problem number 2 looks like the problem that we worked out in class, but can you please explain this in a little bit more? Or can you just outline the steps that we need to take to solve the problem? On the homework and quiz problems, I won't solve the problem all the way to the answers, but I will give you an outline, or I can note down the steps that you need to follow to get to the right answer. Now, if you look at lecture 3 will be discussed by my PhD. He finished his defense, Sushil, and then he would be talking about design of knuckle joint. Then next class is going to be about design of shafts, keys, and couplings. So in today's class, I'm going to talk about design of shafts, but in lesson number 4, we will talk about starting from shafts, how to design keys, and how to design couplings. And please note, so basically, quiz 1 is due. I just want to tell you, I forgot to mention that quiz 1 will be assigned on 7/6. So quiz 1 is due on 7/13. And homework 2 is assigned on that date. So next we will talk about the turnbuckles. Then we will look at the design of turnbuckles. Quiz 2 will be assigned. Homework 2 will be due during that time. A word of caution, for homework 2, you do not have many days. You just have a couple of days for homework 2. That's why there are not many problems in homework 2. So be mindful of that we don't have a lot of time to finish homework too. Then we have design of screw jack. In design of screw jack, you will see design of power screws and other material, that is from chapter 17. Then we have design of springs, which is chapter 23. We will talk about design of helical springs and design of leaf springs. And then there is quiz and homework associated with that. Then we have design of spur gears. We will talk about how to design the spur gears, what are the design considerations. Then we will have design of helical gears. Then we are going to have design of bevel gears. Then we have design of worm gear. And then we have design of internal combustion engine, wherein we will design or we'll try to understand how does an internal combustion engine work and what are the various functional components of internal combustion engine. And if we were to design, how do we design an internal combustion engine? Now, I just want to tell you, even though I have said that these are the basic topics, usually I tend to cover a lot more information in this course. But I want you to have some sort of an outline of the course. So I want to give you this structure. So your homeworks and quizzes will be based on the material that you see under the topic. But typically, I have noticed in the past and last couple of years, I've been teaching this class, that I'm able to cover a lot more material than just these few topics. So typically, I spend some more time on design of internal combustion engine. I actually look at the CAD-based design of internal combustion engine. So there is an engine design software which is known as Lotus Engine Simulation. Lotus Engine, Lotus car is a very good car that is designed by a car company in UK, and their single cylinder engine software is available for free. So we use that and we see how we can design a single cylinder combustion engine. We also look at design of clutch. So that is used in transmissions for clutching and declutching. A very simple example that I want to talk about is if you have a manual car, not automatic, what you need to do is you need to use the clutch so that you can shift the gear, which means you have to decouple engine from the transmission before you change the gears. The other thing that I want to talk about is if you have an air conditioning system in the car, there is something called as electromagnetic clutch. So the air conditioning turns on when that electromagnetic clutch is activated, and that turns the compressor. So the compressor pulley is usually not attached to the compressor, but as soon as you turn the switch on, there is a coil that is magnetized, clutch gets engaged, and then the electromechanical clutch transmits the power from engine to the air conditioning compressor, and your air conditioning system kicks on. Then we talk about the brake design. How do we design the brake? What are the heat dissipation characteristics of brake? What are the different types of brakes? For an example, if you look at your bicycle brake, you would notice some bikes have drum brakes and some bikes have disc brakes. If you look at your cars, some of the older cars, they used to have drum brakes in the front and in the rear. The newer cars have disc brakes in the front and the drum brakes in the rear. and sort of very new cars in last 5-6 years, most of the cars have disc brakes in front and disc brakes in the rear. Then we talk about the pulley design, like V-belt design or flat belt design. We look at the bearing design, sliding contact and rolling contact. All of these chapters are very well discussed in the textbook. So we will follow the textbook pretty much very closely, step by step. And it's a fun book to read. And one thing I want to tell you that this course is one of the most important classes that you will take through your curriculum, because what you will learn in this course, when you go to industry, you would apply. So for an example, if you are working in industry as a design engineer, then you will have to see how to put together a machine component, how to put together a gear train, how to design. So if you go and work for Tesla or Lucid Motors, and you are a powertrain engineer or you are a design engineer, then you will have to design different components. For an example, if you are a maintenance engineer and if you find some faults and if you want to design a replacement, or if you want to select a component that would replace the currently used component, then you would use the material that is discussed in this class. So next section is on the classroom behavior, academic integrity. So please take a look at it. Plagiarism, please don't copy, please work on your own. And if you have any questions or if you need some help, accommodations, let me know. This course is delivered through Canvas. So all the material will be available through Canvas. And what you should do is you should upload your assignments through Canvas. One thing I want to tell you is please don't take pictures and upload the pictures. The easiest way to do is, even if you work out on a piece of paper or engineering paper, or if you type it, everything is acceptable, but just turn it in as one PDF document. Don't turn it in as bunch of pictures, because it's very difficult to grade. So if you have homework 1, just turn in one PDF. You can combine the scans, create one PDF and upload. Now there are scanner apps on the phone, or if you want to use the scanner services at ASU, the scanning services are free. The library and other locations, you can scan and just email that document to your email. Now, let me show you the other resources that are available on Canvas. Any questions related to the syllabus? Any questions at this point? If there are no questions, let me quickly go through the course summary and the assignments that are due. So homework 1 is due on July 6th, quiz 1 on July 13th, homework 2 on July 15th, quiz 2 on July 20th, homework 3 on July 22nd, 27, 29, all the way to August 10. And August 10 is the last day of class. Now, one thing I just want to talk about, if you look at the modules, all the slides for the class, they are already uploaded. So if you want to, so the material that I'm going to discuss today is similar to the material that is discussed in review PowerPoint. It's MP4, its video lecture is also available. So all these material that you need is available on YouTube. It is also available on Canvas. So again, just there is a lot of material. So if you want to follow through the material, just follow one structure. So for an example, if you want to follow summer 20, I would just stick to lesson 1, and so on. or if you want to follow through the YouTube video lectures that are on the syllabus, you are welcome to follow those. The reason for that is these video lectures, I have tried to cover as many problems as I can. So I try to solve different or new problems every time I teach. That way you will have a variety of problems. So for an example, if you are working on a homework, most likely the problem similar to that homework is worked out either in the video lectures or either in the reference notes or somewhere. So what you got to do is just look at the relevant video lectures and try to follow those steps and try to get to the solution. But one thing what I want you to recommend is, for an example, at the end of today's class, please look at the homework and come up with a plan or ask me questions on how to work out the homework problems so that you are prepared and you won't feel stuck while solving the problems. And again, the grades will be posted in the Canvas, and A grade is posted, I think is above 90, B is 80 to 90, C is 70 to 80, and D is 60 and above. So if you look at the syllabus, the grading is also discussed. So any questions at this point related to the course material, related to the syllabus? And if you want to upload, click on the particular assignment, and then what you will do is you will have a button to upload the material. So you are welcome to upload the material. Any questions? Any questions from anyone? Okay, if not, I am gonna start using the whiteboard. So let me so you should be able to see my screen right now. Can you see my screen?
Yes.
Okay, welcome. I'm gonna start the discussion for today's class. So first and foremost, let me talk about what do I mean by mechanical engineering systems. And how is it different than the class that you took earlier? So if you look at EGR445, the class that you took before this class, you most likely studied different components. So how to design maybe a simple bearing, or maybe how to design a bar, or maybe how to design a simple shaft. Now, when we talk about mechanical engineering systems, we are looking at not only the components, but when these components come together, they form an assembly. And what happens is this assembly is used for particular purpose, say for particular application. And in that process, what happens? The forces and other loads, so forces and moments, get transferred from one component to other component. And that gives rise to different conditions of stresses. So in mechanical engineering systems, we are not only looking at finding out stresses in just one component, but we are looking at finding out stresses in multiple components, multiple designs, and so on. So the first and foremost important equation for machine component design is the definition of stress. So stress is given as load divided by area. Now, load is force that is given in newtons. Area is given in meter square. So unit of stress is Newton per meter square, which is also given as pascals. Many a times we use millimeter square. So this unit can also be written as Newton divided by millimeter by 1000 multiplied by millimeter by 1000. So this becomes so 10, so basically to the power 6. So if you want to look at the units of conversion, if you have something like a megapascal, that is nothing but, so if you look at 10 to the power 6 megapascals, 10 to the power 6 pascals is equal to Newton per millimeter square. So 1 megapascal is equal to 1 Newton per millimeter square. Now, there are two ways a stress could be induced. And first of all, let me talk about the relationship between the load and the area. Area could be perpendicular to the load. So what that means is, if you look at an area, and if you look at the force, I'm going to call this F, and this is the area A, then the force is perpendicular to area. This condition is called as the normal load. So normal means perpendicular. So the stresses that are generated are normal stresses. And they are denoted as sigma. So if you look at the normal stresses, there are two types of normal stresses. So let me show you the simple rod. It's a circular cross section, and you have a load P, and you have a load P, and this is called as the rotated cross section. So you have the cross section, but you are drawing the rotated cross section, and this has a diameter D. So if you look at the stress, sigma is equal to P divided by A, which is P divided by pi by 4 D square. Now this P is perpendicular to the area, but this is causing this component to stretch. So as you can see, this is being stretched. So that's why this is called as the tensile stress. Now, if you look at the same component, but rather than pulling, if the load is now pushing, this stress is called as compressive stress. This is compressive. And at this point, I just want to tell you that these two stresses are part of the normal stress. This is normal stress. And why is it normal? Because the load is perpendicular to the area. Now, next thing that I want to talk about, what happens when the load is parallel to area. So for an example, same rod, but the force is like this. So think about like you're cutting an apple or you're trying to shearing it off. In this particular case, the load is parallel to area. And again, the equation is P divided by A, which is P. Area is going to be the same because the diameter is D, pi by 4, D square. This is the load. But this is going to give rise to something called as the shear stress. Because we are trying to shear it off. And these are the very basic stresses. Now, at this point, let me stop a minute and ask you, what other stresses do we know? What other stresses have you studied in the past? Maybe in mechanics of material or engineering design. You can unmute yourself or use the chat window. So what other stresses you know about? Anyone? Any comments? I'm looking at the chat window. Maybe you looked at bending stresses. Maybe you looked at torsional stresses. Maybe you looked at principal stresses. Yep. Maybe you looked at maximum shear stress. Maybe you looked at the hoop stress and so on. But let me tell you, all these stresses are derived from normal and shear stresses. What I mean by that is when you talk about the bending stress is nothing but normal stress. When you talk about torsional stress is nothing but shear stress. When you talk about the longitudinal or hoop stresses, again, that is based on the loading direction. Or when you look at something called as the complementary shear stress, that is a shear stress. So the different stresses that you have studied so far are primarily manifestation or can be classified either as normal stress or as shear stress, with one sort of exception. How many of you, and we will talk about it in lot detail later in today's class, how many of you have looked at something called as principal stresses. Have you looked at principal stresses? Can someone tell me what is a principal stress, or what is a simple definition of principal stress? Anyone? Have you studied principal stress? Have you used the equations for principal stress?
It's the force over the area of a force.
Okay, and I understand. Now I want you to understand this fundamental concept very clearly. There are only two types of stresses. One is normal stress and the other one is shear stress. Normal means the load is perpendicular to area. Shear means load is parallel to area. Now, if you look at the bending stress, what we are assuming is only the normal stress is acting. If you look at the torsional stress, and I want to give you an example. We will work out these problems in today's class, but I want you to look at sort of this example. If you have a beam, and on this beam, you have a moment. What happens because of this moment is that beam bends. And because of that bending, what you have is you have a stress here, you have stress over here, and you have something called as a neutral axis when there is no stress. So you have this called as neutral axis. Now, bending stresses are normal stresses. So basically, the stresses in bending are perpendicular to area. Now, let me give you another example. If you have a shaft, so if you have a shaft and this shaft is twisted, so there is a torque on this shaft and this shaft is twisted. So this stress that is coming on this shaft is purely shear stress. Bending stress is purely normal stress. Now, what happens in the case of principal stresses? Both normal and shear stresses are acting simultaneously. So you have normal stress plus shear stress. And these two stresses give rise to principal stresses. So when you study principal stresses, fundamentally you have to understand principal stresses come into existence because that component is simultaneously subjected to normal and shear stress. Principal stress cannot act in isolation. For principal stress to exist, and let me show you what it means by existence of principal stress, and probably you have seen this diagram before, is you have normal stress, and then you have shear stresses acting over here. So this is the condition for principal stress, which means you have normal and shear stresses acting simultaneously. Now, I want to discuss in detail principal stress a little bit later, but I want you to understand that normal stresses and shear stresses are the only two primary stresses. And when they act together, that gives rise to principal stresses. And then you might have talked about, or you might have studied about different theories of failure. And what does that mean? So you must have studied the Van Mises theory of failure. You might have studied the maximum principal stress theory of failure. You might have studied maximum shear stress theory of failure. So what that means is the calculations that we are doing, they are based on the mathematics. So the mathematical equations we derive are a bunch of numbers, and we either divide, combine, add, subtract, and come up with some formulas. How do these numbers correspond with the experimental observation? Because at the end of the day, what we want as design engineers is we don't want the component to fail. For an example, if you design this lever, or if you design this link, or if you design this chain, you don't want that link to fail or to break when it is subjected to load during its lifetime. So what it means is it should not be able to withstand the static load. If need be, it should be able to withstand the fatigue load. If need be, it should be able to withstand the temperature variation. It should be able to withstand something called as the ratcheting and all other effects that you may or may not know about when you design. So that's why you will realize that the cars are designed so well that they go up to 100,000 miles, 200,000 miles, and the engine or the components inside the internal combustion engine, they are subjected to tremendous amount of loads. That's why you have to select the proper material. You need to have a proper surface treatment. You need to have different types of heat treatments, and then you have to choose different fits or tolerances, so that when the whole components they are assembled and when they come together, they do not give rise to excessive loads or deflection or stresses. So that is what is super important when you design this system. So the point here is, when we design as a design engineer, we can't anticipate all the different types of conditions that component will be subjected to. So what we do is we make some approximations. But as long as those approximations are well within the experiments, those approximations are well within the design intuition guidelines, we are usually okay. So in this class, I will not only talk about the design calculations, but I will talk about how to use some engineering judgment and modify some of those components so that the system is safe when the system is put into use. Any questions? Anytime you have questions, you can raise your hand and ask me questions, or you can type the question in the chat window and I would be happy to answer. So let me tie this to the different design theories that you studied. So the idea here is, these equations like stress, these equations like principal stress, how do we combine and how do we relate these different equations or these numbers that we obtain from these calculations with the experimental result? So we actually have to come with some sort of design theory. In other words, we have to anticipate the different types of failure modes and then relate that failure mode to the design equation. And that relationship between these design calculations and failure mode is nothing but the different design theories. And just to give you a simple example, if you look at the aluminum, if you stretch the aluminum in tensile testing machine, you will always observe that the failure is at 45 degrees. And that is just the material property. And the question is why the material such as aluminum fails at 45 degrees. On the other hand, the material like steel, actually, if you look at the failure, it's 90 degrees. And the reason for that is 45 degrees is the weakest plane for the aluminum, which means even though your loading is axial, the stresses induced at the 45-degree plane is stronger than the material can withstand, and naturally material does not know whether the stress is bending or torsional. The only thing material behaves is as soon as at any point in the material stress exceeds the built-in resistance of the material or the built-in strength of the material is going to fail. And as design engineers, we have to anticipate that, hey, aluminum is weak in 45 degrees. So we should make sure that when we have an aluminum component, either the load does not come at 45 degrees, or if the load comes at 45 degrees, it is much, much less than the failure stress of aluminum. So that is what is needed. So this is something that I want you to understand when we design. And I will write all these notes, but let me give you, let me try to solve a simple problem that will make some of these concepts very clear. So what I want to talk about is just a quick recap, is think about that I have a rod. Now there is a difference between the rod and the shaft, even though the rod and shaft, they are used interchangeably. So I just want to tell you, rod is used to transmit force, and typically shaft is used to transmit force times radius, which is torque. So you have something called as rod and you have something shaft. Now what I want to do is, this is the rod. On this rod, we are applying this load P. And what happens because of this load P? This rod elongates. So this rod is going to elongate. And probably the elongation is uniform on both the sides. So this is the final length. I'm going to call this LF, which is the final length. And there is this initial length, Li. And please note, LF is greater than Li. So here comes the concept of strain. So strain is by definition change in the length divided by original length. So change in the length is L final minus L initial. It's always L final minus L initial divided by the initial length. So this is given as delta L divided by L. It's a dimensionless quantity. Now, one thing that probably you will observe that the material density does not change. So the volume basically, here you see it as the material got elongated, the area would decrease. So something like this would happen. So initial diameter is di and the final diameter is df. So this strain is called as the longitudinal strain. This is epsilon L. Why is it called as the longitudinal strain? Because this is in the direction of length. And you would notice, because of the load that is applied in the longitudinal direction, you have the deformation or you have a change in the lateral direction. This is the longitudinal direction and this is the lateral direction. So what happens is you have the change in the lateral dimension. So I'm going to show you the expression for lateral strain. The lateral strain is again the final diameter minus initial diameter divided by the initial diameter. So change in the diameter divided by the initial diameter. However, I want you to observe that this quantity is negative because the final diameter is less than the initial diameter. df is less than di. Now, at this point, I want to define a concept or a quantity called as Poisson's ratio. Poisson's ratio. Poisson's ratio is the negative of lateral strain divided by longitudinal strain. Poisson's ratio is a positive quantity and usually its value is less than 0.3. So Poisson's ratio is mu, and Poisson's ratio is one of the very important fundamental properties of the material. It gives us the relationship between the lateral and longitudinal change. Now, what I want to do is, I want to tell you that it is interesting to observe if you were to convert this tensile load into compressive load, your longitudinal strain, and I want you to think about this just for a second. So in the case of compressive load, longitudinal strain would be negative, but lateral strain will be positive. Nevertheless, the Poisson's ratio will always be positive. So this is something to keep in mind. The other thing which you probably studied, but I'm going to cover it anyways, is in the elastic limit, ratio of stress versus strain is called as the Young's modulus. Young's modulus. Young's modulus is ratio of stress. This I need to be careful. Longitudinal divided by strain it is longitudinal. And if you look at the equation for stress, Newton per millimeter square, strain is dimensionless, so the Young's modulus is given as Newton per millimeter square or Newton per meter square. Young's modulus is a super important concept in the case of isentropic material. So what I want to do here for a second, let's substitute some values or some numbers. So if Young's modulus is defined as E, okay, stress is defined as sigma, strain is defined as epsilon. What I'm going to do is I'm going to substitute E is equal to sigma, which is P divided by A, and strain is delta over L. So this equation, I want you to observe the way I write this equation. Thus, delta is equal to PL divided by AE. So change in the default or change in the length, it could be tensile or it could be compressive. It's given as force LAE. One thing that I want you to observe, the units, they have to be consistent. So in other words, you cannot add dollars to pesos, dollars to dollars, pesos to pesos, which means if length is in meters, area has to be in meter square, Young's modulus has to be in Newton per meter square, and force has to be in Newton. That will give you the value of delta in meters. If your length is in millimeter, Young's modulus has to be in Newton per millimeter square, area has to be in millimeter square. So you want to be super duper consistent with this equation. And I want to talk about a thought experiment. Say, imagine you have a mild steel component, a mild steel dog bone, and that is held in a tensile testing machine. So what that means is you have one fixed jaw, you have one moving jaw, and what we are going to do is we are slowly going to stretch this component. And initially the length is, this is called as the gauge length. I'm going to call this gauge length as L. This is nothing but the initial length. And as we stretch, this gauge length is going to change. And what we are going to do is we are going to measure two things. We are going to measure the load. So imagine that we have a load cell, and we are going to measure deflection. And if this rod is maybe circular, we probably already know the area, so we know the area. So we are trying to perform a simple experiment wherein we have a rod of known dimension, and what we have is we have a tensile testing machine. In that tensile testing machine, we are going to apply the load, and we are going to measure how much that material is stretching for particular value of load. And what I'm going to do is I'm going to note this load versus deflection combination. So initially, the load is say P0 and there is deflection 0. Then this load becomes P1, I have deflection delta 1. Load becomes P2, the deflection is delta 2. And I continue doing this till this component fails. So I'm going to grab these component in these jaws and pull it hard, very hard till it fails. And I find out what happens to the component. You will realize initially the component is going to stretch. And initially, think about this like a rubber band. You pull the rubber band, you remove the load, the rubber band goes back to its original shape. Same thing happens with this component. You pull the component, remove the load, and the component goes back to its original shape. So this is sort of an elastic behavior. After some time, the component gives up, and what happens is the deformation becomes sort of permanent. So you stretch the component and the component stays stretched. So it sort of reaches the plastic region. And then what you'd observe that component gets overloaded and sort of coning appears. So the cross-section area starts getting reduced and there is high level of stress in this necking area. And after some time, clearly the component fails. And typically you observe sort of cup and cone type of failure. So you would observe as you progress through these loads, all the way to the failure, you would see the component behaving like this. Now, what I'm going to do is, in the next step, I'm going to divide these loads by areas. The initial area, unstretched area. And I'm going to divide the deltas by initial lengths. And what I have here is I have stresses, sigma 0, I have sigma 1, I have sigma 2, I have sigma 3, and I have epsilon 1, epsilon 2, epsilon 3, and so on. So what I have now is I have the pair of stresses, sigma 1, epsilon 1, sigma 2, epsilon 2, sigma 3, epsilon 3, and so on. So what I will do is I will take these numbers and I would plot those on a graph paper. So on x-axis, I'm going to have strain. On y-axis, I will have stress. And you would realize that as I start plotting these points, I get a particular type of curve. This is called as the stress strain curve for mild steel. And you would notice that it has some distinct points. So in the initial region, this is a straight line till something called as the proportionality limit. It means in this region, stress is proportional to strain. And the slope of this line, E, is nothing but sigma divided by epsilon, which is nothing but Young's modulus. Then after this proportionality limit, the stress strain relationship is no longer linear and you would see a little bit of curvature. And what happens is you would notice something called as the upper yield point. And then you will see something called as the lower yield point. And then you will see that the material starts exhibiting more stress, some sort of this type of behavior. So yielding is nothing but giving up. So if you think about the upper yield point, is like material comes to a point that it can no longer withstand the stress. So it starts deforming. And that's why the material yields. And then what happens is, for the same amount of load, the material continues to deform. So which means even though you do not change the load, the material continues to deform, and then it deforms to the point where the necking happens, the stress, the localized stress is significantly high, and then you land up with failure and the component fails. Now this is something called as the engineering stress strain. Why is it called the engineering stress strain? Because the area that we are using to calculate stress is the initial area, and the length that we are using to calculate strain is the initial length. So that's why this is called as the engineering stress strain. But if you go to industry and say if you want to do this experiment slightly differently, what that means is, instead of using the initial area and initial length, if you were to use the instantaneous area and instantaneous length, instantaneous area and instantaneous length, you will not get the stress strain that is shown over here. Instead, you would get a stress strain curve, which is something like this. This is the stress strain curve for the ductile material. So the ductile material are like rubber-like material or springy material or stretchy material. If you were to plot the stress strain curve for a brittle material, you would notice stress strain curve for the brittle material is something like this. Now, what are the typical examples of brittle material? Example is cast iron, graphite, concrete. What are the examples of ductile material? The ductile materials are steel, brass, and copper. So different materials behave differently, and we have to be comfortable with the material properties before we actually select the material. Okay, any questions here? So it's 2:15, and as per the issue rules, after 1 hour 15 minutes, I will have to give you a break of 15 minutes. So I'm gonna give you a break for 15 to 20 minutes, and we'll be back at about 2:30. And I plan on working out a few problems on the material that we discussed, and then continue discussing different types of stresses. So I'm gonna stop recording. Please look at the homework that is assigned for today, and I will be back at about 2:30. Okay, so let me work out a problem. So in this problem, say I have a link, and this is like a chain link. So if you look at the bicycle chain, you will notice the bicycle chain link looks something like this. And I want to show you a rotated cross section. This dimension is 20 millimeter. This dimension is 45 millimeter. This outside diameter is 75 millimeter. And this inside diameter on both the sides, it is 40 millimeter. Now on this chain link, you have load P that is applied, and that load is 45 kilonewton. And what we want to do is, there are two cross sections. One is this cross section, which is cross section A, and the other cross section is this cross section. Cross section B. I want to find out the stresses at A and the stresses at B. Now, one thing I want you to understand is, if you look at the analysis that we are doing in this class, is using mechanics of material principles. So it's simplified. And if you look at the stress distribution, you will notice the stress distribution is usually different. So if you look at the point of location of load, the stresses will be significantly higher. But as you go away from point of application of load, the stress distribution starts becoming uniform. So we are going to assume the stress distribution is uniform under AA and under section BB. So sigma AA is load divided by area. Load is 45 kilonewton. The area is 45 multiplied by 20. And I want you to look at this answer. My answer is 50 Newton per millimeter square. Now let's look at the area BB that we need to find the area, the stress. So let me show you the three-dimensional view. So if you look at the area, this area is something like this, which means 45 10 to the power 3 divided by 75 minus 40, multiplied by 20. This is the cross-sectional area, and the answer, I would encourage you to use your calculators. The answer that I have is 65 Newton per millimeter square. Any questions in this problem? Okay, let me work out the second problem. So, a hydraulic press exerts total load of 3.5 meganewton. So 3.5 10 to the power 6 newtons. And the load is carried, that load is carried by 2 steel bolts. So load is carried by 2 bolts. And the safe stress in bolts is equal to 85 megapascals. And as you know, 1 megapascal is 1 Newton per millimeter square. So 85 Newton per millimeter square. And the Young's modulus, which is the value of E, is 210 kilonewton per millimeter square. So Young's modulus is 210 kilonewton per millimeter square. We have to find out two things. First, diameter of bolts. And the second thing is the extension. So let me show you how that problem is. So what we have is we have a hydraulic press. And this hydraulic press is actually supported by 2 bolts. This hydraulic press is able to exert 3.5 10 to the power 6 newtons of force. This is a large amount of force. And there are 2 bolts. This is bolt 1 and this is bolt 2. We assume both the bolts have circular cross section. They are of same length, and the length is shown in the figure. This length is 2.5 meters. So each bolt is 2.5 meters. And what we want to do is, this is a classic design problem. We have to find out the diameter of the bolt, and we have to find out how far the bolts are extended. So step 1, so to find the stress, we use the equation P divided by A. But since this is a design problem, the value of stress is given to us, value of load is given to us, and we have to find out the diameter. In other words, we have to find out the area. Since there are 2 bolts, (3.5) 10 to the power 6 pi by 4 t square. And when you solve for d, you would realize the answer is 162 millimeter. Now, next step is we have to find out the extension delta. Delta is given by equation PL divided by AE. AE, where P is 3.5 10 to the power 6. Now, please notice the Young's modulus is given in millimeters square. And the load is in Newton. So we need to make sure the units are consistent. So I'm gonna write this unit in millimeter. The area I will write in millimeters square. And Young's modulus, this is very important. I'm gonna write this down as Newton per millimeter square. So this guy, this, and this is in newtons. That way, the answer that you are going to have is going to be in millimeter. So when you work out, your delta is going to be 1.01 millimeters. So please use your calculators. And if you have any questions, just try to check if my answers are correct. Now, let me work out one more problem. Next problem is find the diameter of the pin and the bar. Now, I just want to tell you, this is something similar to a knuckle joint. So what you have is we have something called as the fork end, and we have something called as the eye end. And in between this fork end and I end, we have a pin. And this is a circular rod. This is another circular rod. And the diameter of these two rods is the same. So this is called as the I end. This is called as the forked end. And you have a central pin that is holding, or that is making sure that the I end is connected with the forked end. Now, if you look at the loading, there is a load of 80 kilonewton. That 80 kilonewton load is applied, and the permissible tensile stress, so the say stress for bar, so sigma bar is 100 Newton per millimeter square, and spin is equal to 80 Newton per millimeter square. Now, what I want you to do is, I want you to look at this problem for a minute. And I want to ask you this question. If the bar were to fail, if this bar fails, would it be a tensile failure or would it be a shear failure? So for an example, if that bar has to fail, so you have the I end or the fork end, if it were to fail, would it fail in tension or would it fail in shear? I'm looking at the chat window. So you can type your answers. The bar, not the pin, the bar. So bar is going to fail in tension because look at the rotated cross-section area. This rotated cross-section area is perpendicular to the applied load. So bar would fail in tension. Now let's look at how the pin is going to fail. If you look at the failure mode of the pin, you would notice the pin would fail in double shear. So this is how the pin would fail, which means there would be one area here, one area here. So this would be double shear. So if I want to find out the diameter of the rod, I need to use the equation for the tensile stress. So sigma is equal to P divided by A. Sigma is 100, P is 80, 10 to the power 3 divided by pi by 4 multiplied by d square. And once you solve this, you're gonna get diameter is equal to 32 millimeter. Now, if you are going to look at the pin is going to fail in shear. So it would be tau is equal to P divided by 2 times area of pin is 80 pi by 4 d square. And when you work out the diameter of the pin is going to be 26 millimeter. So please work out these numbers and tell me if these answers make sense. Now let me take one more problem that is based on the stress strain diagram. So this is the next problem. Consider a mild steel rod of diameter is equal to 12 millimeter and tested in tensile tester the gauge length is equal to 60 millimeter. After the tensile testing, this is what we observed. The final length final diameter something called as the yield load, which means the force at which the material yielded. And the ultimate load, which is the load at which the material failed. It's 6.1 kilonewton. So we have to find, with this information, we have to find yield stress, ultimate stress, actually we can find out the Poisson's ratio as well. So let's look at the first and foremost, the value of yield stress. So sigma is equal to P divided by A. The material yielded at 3.4 kilonewtons. The initial area the material failed at 6.1. So this is 30 Newton per millimeter square. This is 54 Newton per millimeter square. And then if you want to find out the longitudinal strain, is the final length minus initial length divided by initial length. Final length is 80. Initial length is the gauge length divided by the gauge length, which is 20 by 60. If you look at the lateral strain, is equal to the final diameter is 7 millimeters, so df minus di divided by di, 7 minus 12 divided by 12, which is minus 5 divided by 12. The Poisson's ratio mu is minus epsilon lateral divided by epsilon longitudinal. So minus 5 divided by 12 divided by 20 by 60. So that is how you can find out the different values. One thing I want to talk about at this point is something called as factor of safety. Factor of safety is the yield stress divided by design stress. Now, this requires a little discussion. So what I want you to think about it is, as an engineer, when we are trying to design a component, or when we are trying to design a structure, or when we are trying to design a machine, we can't anticipate all the possible loading conditions that that component will be subjected to. Many a times, when we start designing, we have some assumptions and we try to design using or based on those assumptions. Unfortunately, under the loading conditions, those assumptions may or may not remain valid. So to sort of error proof or to sort of over design, we take into account something called as the factor of safety. Now, let me explain what is the meaning of factor of safety, starting with our stress strain diagram. So this is the yield point and this is the yield stress. So this is sigma yield. Now, yield stress is the limit because we don't want material to go beyond its yield stress. Because what's going to happen when the material crosses the yield stress? When the material crosses the yield stress, the material deforms permanently, and that may not be desirable. So think about a car, and then you sit in the car, and all of a sudden the car's chassis deforms. You will not feel safe in that car. So you don't want to go all the way up to yielding. You want to be a little bit below the yielding point. So which means your design stress could be at this location, your design stress could be at this location. So this depends upon how comfortable you are with the loading, how comfortable you are with the design, how comfortable you are with the analysis, and again, the material reliability. So for an example, you come up with this great design, but the material that you obtain has some flaws. If it has some blowholes, if it has some impurities, and the material strength is not uniform, then clearly, even though your analysis is good, but unfortunately, since the material does not have the properties that you initially anticipated, the component is going to fail. So then what we need to do is we need to somehow account for that. So what we do is we deliberately reduce the design stress, and that deliberate reduction in design stress is nothing but the factor of safety. So if your yield stress, and let me give you an example, if your yield stress is say 1000 Newton per millimeter square, and as a designer, you say that I'm gonna stick to 100 Newton per millimeter square, then your factor of safety is 1000 divided by 100, that is equal to 10. Now, sometimes such a high factor of safety is not desired, because what happens is if you increase the factor of safety, your component dimension, they become bigger. So the component becomes big and heavy. Now I want you to think about an application such as an aircraft. So for an example, if you are going to design an aircraft, and if you use the factor of safety of 10, then that aircraft is going to be super heavy, and it will increase the cost, the fuel consumption, maintenance, and so on. So you have to strike this fine balance that you want the design to be safe, but don't over design to such an extent that it actually diminishes the very purpose of the design. So if you look at the design data book, there are different guidelines for the factor of safety, which means, for example, aerospace application, they will suggest certain factor of safety. For locomotive applications, they will suggest certain factor of safety. For automotive applications, they will subject that there will be some factor of safety. So what you do is you usually refer to the design data book or the design guidelines and select the appropriate factor of safety. And with this newer analysis tools like finite element analysis, CFD analysis, we are able to analyze more accurately, and that reduces the need for very high factor of safety. But engineers always try to design or make an error on the side of caution and use factor of safety that is typically uh, provided in the design handbook. So selecting a proper factor of safety is an important concept, and you should always be mindful of the application, the material, and the type of loading conditions that the material will be subjected to come up with appropriate factor of safety. Okay, now with this, what I want to do is I want to touch upon something called as the thermal stress. So if you look at the thermal stress is an interesting concept. Consider a rod, and this rod maybe is left in the sun and gets hot. And what happens? Because of the heat, the rod gets extended. So its initial length was Li. Because of the temperature, its final length became Lf. So at this point, this has thermal strain. So which means Lf minus Li divided by Li. This has thermal strain, but there is no stress. Now consider a slightly different case. Same rod, but this rod is held in between the supports. So these supports are rigid. These supports are not moving. So what happens is, same thing. Because of the rise in temperature, the rod extends. Rod tries to extend, but these supports hold this rod together. They do not let it stretch. And because of that, there is a thermal stress. And this thermal stress is nothing but the Young's modulus multiplied by the thermal strain. So this is Young's modulus. And I just want to give you an expression for thermal expansion. So delta thermal is equal to alpha times L times delta T. And thermal stress and epsilon thermal is alpha L delta T divided by L. So alpha times delta T. And thermal stress is the Young's modulus times alpha times delta T. So thermal stresses, they are applied or they come into existence when you have a component that is subjected to change in the temperature. The component expands and there is a support that is going to prevent its expansion. Thus, prevention and expansion would cause the support to exert some force, and that force divided by area is equal to nothing but the stress that is induced in the thermal component, in the component. Any questions at this point? Any questions on the material that is discussed so far? Okay, so what I want to do now is I want to talk about torsional and bending stresses. So before I do torsional bending stresses, understand torsional stresses and bending stresses, they are manifestation of normal and shear stresses. So bending stress is nothing but due to normal stress, and torsional stress is nothing but because of the shearing or the shear stress. So Next topic that I want to talk about is torsional and bending stresses. And this is nothing but chapter 5 from your textbook. So let's look at first the bending stress. So what happens is, think about like you have this beam and this is a rectangular beam. And what we do is we apply forces on this rectangular beam. And because of the forces, this beam bends. So say you applied force that gave rise to a moment and the beam bent. Now I want you to look at what happens at the top versus what happened at the bottom. So if you look at the top, the fibers on the top are compressed. What this means is, I want you to think about A, B, and I'm going to have A dash, B dash. So the length A dash, B dash is less than length AB. So in other words, the fibers on the top of the beam shrinks. Now I want you to look at the bottom of the beam, which is C, D, and C dash, D dash. The bottom of the beam expands. So which means C dash, D dash is greater than C, D. So what this means is there is compression on top and elongation on bottom. And at this point, I just want to take a moment to talk about where the normal stresses are acting, because that is super important. And most likely all of you have looked at this particular bending beam and the famous equation that comes after that. I just want to tell you where the stresses are. Now, for that, it may be instructive to draw a three-dimensional view of this beam. So what I'm trying to draw here is the three-dimensional view. So this is the same beam, but in 3 dimensions. Now this is the top. This is the bottom. So all the fibers here are kind of compressed. So I'm going to show you the load lines. And if you look at the bottom, the fiber here, they are stretched. So if you look at the load lines are going in the opposite direction. So what it means is there would be a one fiber where the beam will neither be stretched nor be compressed. So there will be, say, I'm going to call this EF. So EF is equal to AB is equal to CD. So in other words, there is going to be one plane or one fiber its length is not going to change from the initial undeformed length. And that is called as the neutral axis. Why it is called as neutral axis? Because it does not deform. So this is called as the neutral axis because this does not deform. And if you were to show the neutral axis here, I'm going to try to show the neutral axis here. This becomes sort of a plane. So if you look at the load on the top of the neutral axis, it is like this. If you look at the load at the bottom of neutral axis, it looks like this. So what I want you to do is, I want you to look at the cross section. I'm going to show it as PQRS. So this is P, this is Q, this is R, and this is S. So I want you to look at this cross section, and you will notice above the neutral axis, this cross section is compressed. So there is compressive load, and below the neutral axis, this cross section is stretched. So there is tensile load. So if I were to show the distribution of the stress, then you will notice on the top, it's compression, and at the bottom, this is tension. And the variation is linear. There is no stress at the neutral axis. No stress at the neutral axis, but the variation is triangular, and there is compression on the top and the tension at the bottom. So the load, basically the stress, is on the plane which is perpendicular to the load that is shown over here. So remember this, because this is very important when we look at the design of levers. And the equation that we use to solve the bending stress problem is given as M divided by I is equal to sigma divided by Y is equal to E divided by R. So what that means is M is the bending moment, I is the moment of inertia, sigma is the bending stress, and that bending stress could be tensile or compressive. And Y is the distance from neutral axis, then I need to write what E is. E is the Young's modulus, and R is the radius of curvature. Now, what is moment of inertia? Moment of inertia is something called as the second moment of area. And I will give you the expression for the moment of inertia for a rectangular cross section. So you have this rectangular cross section and say this is the neutral axis, or the moment is about this neutral axis. So this dimension is usually called as B, and this dimension is called as D. And the moment of inertia about neutral axis is BD cube by 12. If you have a circular cross section, the moment of inertia about any diametric cross section is going to be the same. This is the diameter D. So moment of inertia is pi d raised to 4 pi 64. Now let's look at a hollow cross section. If you have a hollow cross section, this is the neutral axis. This is B1. This is D1. This is B2. And this is D2. Moment of inertia is outside cross section moment of inertia minus inside cross section moment of inertia. Same thing with the circular cross section. If this is D outside, D inside, it is the moment of inertia of the outside cross section minus moment of inertia of inside cross section. Now the next question is, how do you find the moments? So to find moment is nothing but force multiplied by distance. And let me give you a very simple example. If you have a cantilever beam, and say there is a force here, at the length of the beam is L, the maximum moment is going to be at this section O. So if you were to draw the bending moment diagram, this is how it's going to look like. This will be F times L. So if you look at this cross-sectional area XX, if this distance is X, the moment at XX or bending moment at XX is going to be F times X. Now similarly, if you were to have a simply supported beam, and if there is a load at the center span, then what you need to do is, if this is the force F, that force is divided equally. And if you want to find out the bending moment at the center span cross section, so bending moment at section XX is F2 F by 2 multiplied by, if this distance is L, the center is at distance L by 2, so L by 2, it becomes F times L divided by 4. And you could have slightly different loading conditions. And if you have slightly different loading conditions, the standard way to solve those types of problems is draw the shear force and bending moment diagram and find the maximum bending moment. Now, y is the distance from the neutral axis. So let me take a couple of examples on bending loads, and then we should be able to solve for the bending stresses and then use the design equations. So before I start, I just want to ask you any questions here. Any questions here? Okay to go with bending stress problems? I don't see any comments, so I'm gonna assume we are all good. And I'm going to work out a problem. So consider the beam. Shown in the figure. So what we have is, in this beam, there is this load 400 Newton, and this beam is of rectangular cross section, and this is the dimension D. So yeah, this is the dimension D, and this is the dimension B. And what they are saying is D is equal to 2 times B. So this is the cantilever beam, and the load is 400 Newton that is acting at the 300 millimeter, and the depth of the beam is 2 times the width of the beam. And we have to find out the dimension B and D, when the sigma design or the maximum bending stress is limited to 40 Newton per millimeter square. So the maximum bending stress is limited to 40 Newton per millimeter square, and the beam is cantilevered and the load is 400 newtons, and this load is not acting at the end. This load is acting at the distance 300 millimeter from the support, and this is something to take a note of. I mean, the beam is longer than 300 millimeters, but this load is acting at 300 millimeter. So let's work out this problem. So we have to find out the bending stress. Remember the equation, m divided by I is equal to sigma divided by y. So sigma is equal to m divided by I multiplied by y. So since this is a symmetric beam, the neutral axis is going to be here. So the bending moment is going to be 400 multiplied by 300. Now the value of I is BD cube by 12. And y is this distance. The maximum distance is from half of the dimension D, or from the neutral axis. So this is going to be D divided by 2. And the design stress is given as 40 Newton per millimeter square. So the design stress is given as 40 Newton per millimeter square. And if you look at this overall setup, let me simplify this equation a bit. 400, 300 divided by B D square multiplied by 12 multiplied by 2. And if you look at the equation, D is equal to 2 times B. So what I would do is I would substitute the value of D is equal to 2 times B, and then my equation becomes 400, 300 multiplied by 12, B multiplied by 2B square multiplied by 2 is equal to 40. And if you look at this entire equation, the only unknown is the value of B. And when you solve, value I got is 17 millimeter. Value of D is 34 millimeter. So any questions on how this problem is worked out? Let me take one more problem. So we have something called as an L bracket. So again, if you study bracket design, or lever design, the principle that we used to design a bracket or design a lever is the same as the bending stress concepts. So what I'm trying to do here is I'm trying to design a bracket, and this bracket is loaded as shown in the figure. So this distance is 100. This is the rotated cross section, and this dimension is D. This dimension is B. Just like the previous problem, D is equal to 2 times B. And in this particular case, the bending stress sigma design is equal to, again, 40 Newton per millimeter square. And value of P is 100 Newtons. So the question here is, I want to design this bracket and find out the dimension of this bracket. So first and foremost, I want you to understand that because of this loading, this bracket is going to bend like this. So in other words, the cross section that is shown is going to bend. And the equation that we are going to use is sigma B is equal to M divided by I multiplied by Y. So the bending moment is going to be load multiplied by the distance, 100 multiplied by 100. So this is P and this is L, divided by the value of I. Again, it's a rectangular cross section, so it's going to be BD cube by 12 multiplied by the distance from the neutral axis, which is D by 2. And here you will have the same equation divided by BD square multiplied by 12 divided by 2. And in this equation again, you have to replace value of D is equal to 2B and solve and find out the value of B. Once you know the value of B, you should be able to find out the value of D. Any questions here? Okay, I would, if you have a calculator, please work out this problem and then find the numbers. One thing you have to keep in mind is dollars to dollars, pesos to pesos. So make sure all the units are consistent when you find out the answers. Let me take this discussion a little bit further and discuss something called as the lever design. This is chapter 15 from your textbook. So lever design is nothing but a straightforward extension of the the bending stresses. And what I'm going to do is I'm going to work out some simple problems for the lever design. That way you would be comfortable with the design process, whether it's a bending support, whether it's a bracket, it's a lever, or maybe it's a combination. The only thing that I want to talk about in the design of lever is a new concept which is called as the bearing stress. Now, what is this bearing stress? So bearing stress comes because of the bearing. So for example, if you have a rod or if you have a shaft, and this rod or the shaft is supported in some sort of a journal bearing. So this is the journal bearing, and this is where the rod or the shaft is supported. So what happens is, at this interface, and I want you to follow this very closely, at this interface, the stresses are significantly higher. So the stresses at these interfaces, so these are the interface stress, and this is known as the bearing stress. Okay, 3:45. So again, after 1 hour 15 minutes, I have to give you a break as per issue requirements. So I'm going to stop here and I will pick up from here at 4 o'clock. So a break for 15 minutes. So let me talk about the concept of bearing stress. Now, what I want you to do is, I want you to think about, say, if you have a shaft or if you have a rod that is supported in some sort of a bearing. Usually this is called as the journal. Then if you look at the stress distribution, the stress distribution is going to be like this. So this is the stress distribution. And if you have a load P that is coming on top of it, now the question is, how do you design this journal? So how do you find out the length of the journal or the diameter of the journal? So for that, let me talk about something called as an approximation of the bearing stress. So what we do is, for practical purposes, we assume that this distribution is not the circular as I shown, but sort of uniform and rectangular. So what we look at is, we look at the projected area. So this is the rod, and this rod is supported in this journal. This rod is supported in a journal. So what we do, and this is a sort of an engineering convenience, is we look at the projected area. This length is L. This is diameter D. So the projected area So the bearing stress is equal to P divided by area projected and P divided by D multiplied by L. And D times L is the projected area. So whenever we talk about the design of bearing, or when we talk about the lever, and when we talk about the pin, it is usually designed using the bearing considerations. So let me take a lever design problem and things will be clear. So design the bell crank lever as shown in picture. Find dimensions of the cross section and pin diameters. And this lever looks something like this. Now, an interesting observation here, this is called as the bell crank lever. And there is some historical meaning to this bell crank lever. So if you look at the church bells, what they used to do is they used to have a lever, something like this. And then there used to be a rope. So to ring the bell or the toll the bell, what people used to do is pull on this rope. And this perpendicular lever, this could be perpendicular or this could be at an angle, but this lever would actually hit the bell and generate that sound. So that's why this lever is called as the bell crank lever. So let me draw this bell. And that's why this is called as the bell crank lever. Now, if you look at this bell crank lever, the dimension of this bell crank lever, this dimension is 500 millimeters. This dimension is 150 millimeters. And the load here is 4.5 kilonewtons. So this load is 4.5 kilonewton. And this cross section they are perpendicular to each other. This cross section, they are perpendicular to each other, and we have to find out the cross sectional area or the dimension of the cross section. This dimension is D, this dimension is B, and what we want to do is we want to find out not only the dimension B and D, but here is something called as dP, which is diameter of pin. Now the safe stress in tension, sigma T design is equal to 75 Newton per millimeter square. Safe bearing stress, which is designed, is 10 Newton per millimeter square. And with this information, we have to design this lever. So if you think about this lever, this can be assumed or this can be approximated as a cantilever beam. So sigma B is equal to M divided by I multiplied by Y. And in this particular case, we have to make an assumption, and that assumption is the ratio of B and D. So basically, we need to find out, because there are going to be two unknowns. So one of them has to be expressed in terms of other unknown. Only then that equation could potentially be solved. So I'm going to assume, and please note, this is a design. So I'm going to assume that B is equal to D by 4. This is an assumption. So sigma B, it's 75, is equal to 4.5, 10 to the power 3, multiplied by distance 500, divided by I, which is BD cube by 12, multiplied by D by 2. This equation can now be expressed as 4.5, 10 to the power 3 times 500 divided by B, which is D by 4 multiplied by D square. So the only unknown in this equation is the value of D. Once you know the value of D, value of B can be found out. So with this, one part of the lever can be designed. Now, some of you may ask me, what about this cross section? So if you really want to design this cross section, it is possible to do that. For that, what you will do is something like this. Look at the free body diagram of this lever. This distance is 500. This distance is 150. The load here is 500. So this you can find out the load P. Taking the moment about the fulcrum or the hinge, P multiplied by 150 is equal to 500, 4.5 kilonewton. This is 4.5 kilonewton. 500 multiplied by 4.5 kilonewton. That gives you the value of P. But recognize, at the end of the day, the moment that is coming on this cross section is going to be the same as 500 multiplied by 4.5, which means the same dimensions would be valid on the top side of the beam. The only difference here is, if you look at 4.5 divided by 150 multiplied by 500, so this is, so 0.3 times 50, so this will be 15 kilonewton. The only thing is, if you take the force 15 kilonewton multiplied by 150, the moment is going to be the same. And same cross section dimensions would work. Now, next part is design of pin. And I want you to think about the total load on the pin. The total load on the pin, if you were to draw the free body diagram on the pin, you are going to have 4.5 kilonewtons going down and 15 kilonewtons going in the left direction. So the total load, which is the resultant, is going to be the square root of 4.5 square plus 15 square. So that will be the total load, that is the resultant load on the pin. And I want to look at how this pin is going to look like. And let me show you the three-dimensional view of this bell crank lever. So we have a hole here, we have this big hole here. So if you look at this pin is going to go through this central hole. So if you look at this thickness is nothing but the value of B. This dimension is B, and this is the diameter D. Please note B is known, and I did not calculate the actual value of B, but please try to understand from the last step, we should be able to find out the value of B. So B is known. So the bearing stress sigma B is equal to R divided by B multiplied by the diameter of the pin. So the value of R is known. Value of bearing stress is given to us, which is 10. So the value of the bearing stress is given as 10. Value of B is known. Value of R is known. R comes from here. B comes from the previous step. And the only unknown in this equation is the diameter of the pin. So that way you should be able to find out the diameter of the pin. And most of the lever problems are some variations of this. So what you need to do is you have to look at the different forces, find out the moment, and then use the equation for moment and find out the dimensions. With this, I'm going to stop here. And if you have any questions, I would be happy to answer on the material that we discussed so far. So quick recap, we looked at chapter 4. We looked at the syllabus introduction. We looked at chapter 5 partially. We looked at the bending stresses, and we extended the discussion on the bending stresses to design of supports or design of brackets, and we looked at the design of levers. So we have covered about 2.5 chapters in today's class, plus a little bit of introduction. Please review the material, and you should be able to work out the homework problem so far. So I will ask you to just quickly open up the homework document and tell me if you have any questions on working through the homework problems. And if there are no questions, that is for today. I will see you again on Tuesday, and I plan to upload this PowerPoint slides and the video lecture. So that's it for today, and I will see you again Tuesday at 1 o'clock. If you have any questions and if you want to meet in person, I would be on campus all day tomorrow. So you are welcome to send me an email and stop by my office, and I would be happy to discuss the material with you. Thank you very much and have a good evening.